we now have a goal in mind for what we want to do with these or how we want to count them. So a lot of the times that you're trying to calculate the dimension of some vector space, you're going to probably be using the rank nullity theorem a lot. And so I think that this section in particular highlights how useful the rank nullity theorem can be, and maybe that's one thing that I think is really good to take away from this section, other than just the general, magic squares are kind of interesting, sort of, whatever. So anyway, how are we going to use the rank nullity theorem here? Well, let me start by saying the goal for the first thing I want to do, the claim is that the dimension of mn is equal to the dimension of mn0 plus 1. Remember, this is the just set of n by n magic squares, and this is the set of n by n magic squares whose magic number is 0. So here's the idea. Consider the trace map. It's denoted by TR for trace, and it's a map from the n by n magic squares to R. Really, the trace map is a map from n by n matrices to R, but we are just going to be restricting our attention to mn so that we can apply the rank nullity theorem. The trace map is given by the following. So the trace of a matrix whose entries are mij, and I and j are ranging over 1 through n, both of them. So the trace of a matrix is going to be the sum of its diagonal entries, and if the entries are mij, then this is going to be equal to m11 plus m22 plus all the way up through mnn. So yeah, really all this map is doing is taking a matrix and it's adding up its diagonal entries. So if you take the trace of a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, let's take the trace of this matrix. It's just the sum of the diagonals, which would be 1, 5, and 9, and then this would be 15 in this case. Okay, cool. Great. So let's see. Do I want to do this? Yeah. Okay. So the null space of the trace map is the following. So the null space, just by definition, is going to be the set of matrices in M sub n such that the sum of its diagonal entries is equal to 0. But hey, the sum of the diagonal is, that's just like one of the sums that you're looking at when you're doing magic squares. So the sum of the diagonal entries is equal to the magic number for a magic square. And so the null space is quite literally the set of magic squares whose magic number is 0. So in other words, the null space is equal to m sub n0, because that's just definition of what mn0 is. This is a set of magic squares with magic number 0. Okay. Also, note that the trace function is onto, the trace map is onto. Why is this? So trace map is from mn to r. So to show that it's onto, we need to show that for any r in our codomain R, that there is some matrix, that there is some magic square that maps to R, whose trace is equal to R. So we're working with n by n matrices. So we've already talked about that you could just make a matrix where all of the entries are the same, and that would be a magic square. So let's do that. So for each entry, maybe you would think just, okay, make each entry equal to R, and then what is the trace of that going to be? So this isn't going to work, but the trace of the matrix where all of the entries are R would be, well, this is an n by n matrix. So this is an n by n matrix. So this would be the sum of the diagonal entries, and there would be n of them. So this would be n times R. So to fix that, what we can do is just divide each entry by n, the size of this matrix. And so all of the entries are just going to be whatever our R is divided by the size of this matrix, n. So if I do this, now this will fix our issue, because now I add up R over n plus R over n plus R over n. And how many times am I doing this? Well, if this is an n by n matrix, then there would be n of these things, and so this is n times R over n, which is equal to R. So for any R in our codomain, there is a magic square whose trace is equal to that R that we're asking for. So this is an onto function. All right, and now we have enough to apply the rank nullity theorem to the trace map. So the trace map is from Mn to R. So the rank nullity theorem quite literally says that the rank of the trace function plus the nullity of the trace function is equal to the dimension of the domain of the function we're looking at, which is Mn. Okay. The rank is the dimension of the range space. So because the trace function, the trace map maps onto R, the range space is equal to R itself. And so the dimension of the range space is just 1. If this were not an onto map, then the rank would be equal to 0. But because this is an onto function from some vector space to R, then the rank has to be 1. Okay. The nullity is, so we already said that the null space is equal to m sub n0. And so the nullity is the dimension of the null space, which is the dimension of m sub n0. And so taking into account all of the things that we said so far, we have now shown that 1 plus the dimension of m sub n0 is equal to the dimension of m sub n. And I think I said at the beginning of this whole discussion that that's what our goal was. That's what our claim was. And so our claim that the dimension of m sub n is equal to the dimension of mn0 plus 1, we have now proven this. And so in the next video, what I want to do is show you